Today we've got our last section in chapter 5, 5.3, which means we only have 2 chapters left to go, right? 6 and 7. But before we start chapter 6, we've got 5.3 to do. It will continue on this idea of using derivatives to figure out where a function is increasing and decreasing, identifying the critical numbers, and then asking this question of, are these critical numbers maximums or minimums, or neither? So we'll examine this question a little bit more. But before we do, let's consider this simple polynomial here. I've got f of x is 3x to the fourth plus 12x squared minus 5x plus 3. And what's one thing we can do with functions? Well, we differentiate them, right? So I've differentiated this polynomial. The derivative 3 times 4 is 12, 12x cubed. 12 times 2 is 24 times x to the 1 minus 5. All right, so there's our derivative. Well, the derivative is also a polynomial. Right? It's also a function, and what can we do with functions? We can differentiate them. So in comes this notion of, this is usually called the first derivative, f prime of x. There's the first derivative, right? Because I've differentiated f, but I've only done it once. I've got my first derivative, but I can differentiate it again. So we get what's called the second derivative, and this is usually denoted as f double prime. Right? So 2 marks here to indicate I'm differentiating twice. It's the derivative of the derivative. So I differentiate f prime to get 12 times 3 is 36x squared plus 24 times 1, so 24, minus 0. So I differentiate f to get the first derivative of f prime, but if I differentiate that again, then I get the second derivative of f double prime. So here's the second derivative. Well, hold on, this is a function. What do I do with functions? I differentiate them. So how about I differentiate this again? What do we get? We get the third derivative. It's f triple prime. So derivative of this guy is 36 times 2 is 72x plus 0. And I can keep playing this game, right? This is the third derivative. This is the third derivative. And I can keep playing this game. This is a function. I can differentiate that, so I get the fourth derivative. At this point, the prime notation starts to become kind of ugly, right? You don't want to have to count how many primes there are here, so people tend to start putting them in brackets. A little 4 up here to indicate it's 4 derivatives. Inside the brackets, the parentheses here sort of universally indicate that I'm doing derivatives. I'm not like raising the function to the power of 4 or something. So I differentiate the third derivative to get the fourth derivative, and that would just be 72. So there's the fourth derivative. And you can see what's going to happen from here on out, right? If I take the fifth derivative, derivative of 72 would just be 0. And in general, let's see if I can fit it, the nth derivative, where n is at least as big as 5, is always 0, right? So this is for n bigger than or equal to 5. So this would be the fifth derivative. Or in general, the nth derivative. All right, so there is more, there's this notion of not just differentiating once, differentiating several times. The second derivative, the third, the fourth, it means just differentiate again and again and again and again. Let me point out some additional notation here. Right, so we had y equals f of x, and then we've got f double prime of x, and I said there's notation for the second derivative. Alright, so we're just making some notation remarks. Well, what other notation might you see? Here's one I don't often use, but remember when we talked about derivatives originally, sometimes people use a capital D, sometimes with a subscript here, to indicate that I'm differentiating with respect to x. And this would be notation for, that's an ugly parenthesis. This would be a notation for the first derivative. You want to do it twice, just put a 2 up there. So it's the second derivative. Well, what about the Leibniz notation, right? Remember this dy over dx stuff? Well, the second derivative is the derivative of the derivative, right? So this says differentiate y and then differentiate it again, and this is very long-winded notation. People tend to not write it like this. They tend to combine these. So what do I have? I've got d up top applied twice, so it's d squared over dx applied twice over dx squared. The dx is considered to be a single object, so the squared is applying to both pieces. It's not just an x here. Dx is just one thing, despite having two characters representing it. So that's just one thing of y. Or, quite often, as in dy over dx, the y ends up top. So there's d squared y over dx squared. That's the Leibniz notation. It tends to be a little bit clunky for second order derivatives, but you will see this from time to time as well. Although if I have a choice, I tend to just stick to the Newtonian priming notation because it's cleaner. Alright, so let's do an example here. Let's see, let's do a physics example. Suppose the distance of a particle from its starting point, suppose the distance of a particle from its starting point at time t is given by the following function. Remember these distance functions, we tend to use s, so I'll call it s of t is t squared minus 1 squared minus 1. Sort of a silly way to write that function. If you squared this out and just wrote it as a simple polynomial, it would look prettier. But we'll leave it in that form. So there's the distance of the particle from its starting point given by this function. You plug in a time t, and it outputs the distance that you are from your starting point. Notice, by the way, if you plug in t equals 0, you will indeed get minus 1 squared, so positive 1 minus 1, which is 0. So that's what you would expect at time equals 0. It's at its starting point. And let's see, what do? Well, we differentiate this, right? If I differentiate the distance from its starting point, if I differentiate a distance function, the rate of change of distance, I get velocity, right? So the velocity at time t is, people usually call it v of t for velocity, but what is it? It's the rate of change of position, right? So it's the derivative of position, it's s prime. And if I differentiate this using, let's see, what do I need to do here? I need to use the chain rule, right? I've got a function of t that's then all squared. So under the chain rule, special case number 1, the 2 comes outside, inside stays the same, power lowers by 1, so to the power 1, and then multiplied by the derivative of the inside, right? The second half of the chain rule says now I have to multiply by the derivative of the inside, so times 2t, minus the derivative of 1, which is 0, and if I clean this up, I've got 4t times t squared minus 1. So there's the velocity function. It's the rate of change of position. It's the derivative of position. But what if I differentiate it again? What if I took the second derivative of position? The rate of change of the rate of change. Well, the second derivative would be the rate of change of velocity, right? Second derivative of s would be first derivative of v, so the rate of change of velocity. What's the rate of change of velocity physically? It's your acceleration, right? So the acceleration at time t is, let's see, I don't have a whole lot of space here, so we'll do it down here. I'll call it the function a of t, a for acceleration. Well, it's the derivative of velocity, which means it's the second derivative of position. And to find this, I just need to differentiate the velocity function, right, which amounts to differentiating position twice. The velocity function right now is written as a product. How about we just write this as a simple polynomial? This is 4t cubed minus 4t, and then it's easier to differentiate, right? As a product, I'd have to use the product rule. Written like this, I can just differentiate straight away. 4 times 3 is 12t squared minus 4. So there's my acceleration function. Right, so this is sort of the physical interpretation of these higher order derivatives, right? It's the rate of change of the rate of change, and if you interpret your function as being position, then the first derivative is velocity, second derivative is acceleration. And third derivative, people don't usually talk about it, but it actually has a name. The rate of change of acceleration, the third derivative of position, is sometimes called the jerk. So we're going to talk a little bit now about how these higher order derivatives affect the shape of a graph. And we already know the first derivative tells us about whether a function is increasing or decreasing, right? But there's actually multiple ways that a function might increase. For example, I'll put this one in the middle, and I'd really like to do two rows here. Let's see. Draw it a little bit smaller. In fact, I don't like this either. Okay. Let's put our axis way down there. All right. There's an increasing function, right? As you move from left to right, your y values get bigger. It's an increasing function. But not all increasing functions look like that. That's just a linear increasing function. Here's another way a function might increase. And the difference here is it's no longer linear, it looks parabolic or something, but it's increasing and it gets steeper. As you move from left to right, the steepness of this graph is also increasing. And on the opposite hand, you might increase, but you might start increasing at a slower rate. Okay, this one's increasing, but the steepness is actually decreasing. So 1, 2, and 3. There's 3 different ways a function might increase. The graphs will look very different in their shape, and similarly, you can decrease in different ways as well. Right? Here's a decreasing function. Maybe I should have gone with the middle one first. Here's a linear decreasing function. Here's one that's decreasing, but the steepness is also decreasing as you decline, right? Well, maybe I shouldn't say the steepness is decreasing. The steepness is tending towards 0, right? It's actually increasing in the positive direction. And over here, here's a function that's decreasing, but it's getting more and more negatively steep. So 1, 2, and 3. And as I look at this one, it's a little bit too flat there. Okay, so 3 increasing functions, 3 decreasing functions. They all have very different shapes, but we have names for these types of increasing and decreasing functions. Over here, the way that these two increase or decrease, they increase and decrease in what's called a concave up fashion. So this is concave up. And I'll give you a definition for what this means in a second. Over here, these two guys, they're increasing and decreasing respectively, but they're both doing it in a concave down fashion. So these concave down. So what does it mean to be concave up? Why is this concave up? Well, suppose I came into any point on either of these graphs. If I came into any point and I put down a tangent line on either of these graphs, you'll notice that the graph is always above the tangent line, right? No matter where I try to draw a tangent line, the graph is always above it. So here's what it means to be concave up. It means the graph is always above its tangent lines. Always above the tangent lines. And over there, the concave down ones, it's the opposite phenomenon is happening, right? If you come in and you put down a tangent line anywhere, no matter where you try to put down a tangent line, the graph is always below its tangent lines. Right, so over here, the graph is always below its tangent lines. So there's a formal definition, but in truth I tend to just think of this as in terms of the shape, right? I think of concave up as if I were to pour water on this, would the graph catch it? And the answer is yes. Meanwhile, concave down, no, it would sort of run off, right? Concave up graphs tend to sort of want to form a bowl shape, while concave down is the opposite direction. It forms a dome shape. Alright, so here's one more bit of terminology. Here's a function, y equals f of x. And if I asked you if it's increasing or decreasing, hopefully you'd agree this is an increasing function, right? It's always increasing. Always increasing. But what about the concavity? Well, the interesting point probably happens right around here. Let's say this is x equals a, and there's the point on the graph a and f of a. Well, what about to the left of a? To the left of a, this is forming this dome shape, so this is a concave down function over here. Right, so it's concave down. It's concave down on minus infinity up to the point a. But once it passes a, it actually changes shape, right? It's still increasing. It's still an increasing function, but now it's forming this bowl shape. Now it's increasing up, or sorry, it's not increasing up. It's concave up, right? So it's concave up on a to positive infinity. Right? So graphs can do this. They can switch concavity. Meanwhile, just staying increasing or decreasing the whole time, the concavity can switch on you. And the point where it switches concavity, these are interesting enough to warrant names. This is called a point of inflection, or an inflection point. So, point on graph, A and f of A, where concavity changes, is called a point of inflection. Or, a little bit shorter, just an inflection point. Alright, so this happens, right? Concavity can switch, and the point where the concavity switches is called an inflection point. So what you can do now is hopefully recognize from the shape of a graph whether it's concave up or concave down. And I've given you this formal definition of concave up means it's always above the tangent lines, and concave down is the graph always lives below the tangent lines. But the way you should really be thinking about this is in terms of rates of change. So concave up, right? What did I say? Concave up means, okay, it's always, the graph always lives above the tangent line. But what does that mean? Well, that means that the slope is increasing, right? Even over here, it's easier to see that the slope is increasing for an increasing function, but even over here, right? Even over here, at this point it has negative slope, and over here it's got less negative slope. So the slope is still increasing. Right, so concave up means that the slope is increasing. But what is the slope? Well, the slope is the derivative, right? And this says that the derivative is increasing. Well, if something's increasing, what does that mean? That means its own derivative has to be positive, right? So this might require you to do some thought, right? You might need to stop and think about this for a little while. But the slope is the derivative, the first derivative, and I know that's increasing. So that means the derivative of the derivative has got to be positive. So hence, the second derivative has to be positive. Right? Because this is the derivative of f prime, and since f prime is increasing, the derivative of f prime has to be positive. And similarly, you can reason this out over here. Concave down means that the slope is decreasing. So hence, the second derivative has to be negative. And this really does. The first time you work with this stuff, the first time you think about it, you really do have to spend a little bit of time reasoning this out, right? If the slope is increasing, why does that mean the second derivative has to be positive? Well, because this is the derivative of the derivative. And the derivative tells us whether something is increasing or not. So spend a little time thinking about this, making sure you understand why this follows. But even so, we're going to turn this into a simple test for concavity. We can use these two facts to figure out when a function is concave up or concave down. And then I'll be able to tell you why it's actually useful to know these things. So here's the test for concavity. Test for concavity. Here's the test. 1, f of x is concave up. F of x is concave up on an interval if, as we just saw, if the second derivative is positive on an interval. And 2, the opposite statement, f of x is concave down on an interval if the second derivative is negative on that interval. So already we're seeing these higher order derivatives come into play. They tell us something useful. The first derivative just tells us is our function increasing or decreasing. The second derivative tells us more about the shape of the graph, right? There's many ways a function can increase or decrease, 3 different ways as we saw. And the second derivative tells us about the way it increases or decreases, the shape of the graph. Is it concave up or concave down? So if I want to know if a function is concave up or down, I just need to ask when is the second derivative positive or negative. And the way we do that is very similar to the way we asked is our function increasing or decreasing. We've solved inequalities before in the last couple of sections. And so here's a simple example. Let's say find where f of x is, oops, I should tell you what f of x actually is. f of x is x to the fifth minus 30x cubed. Find where this is concave up, or down. And when we do this, we'll be able to list all the inflection points too. So concave up or down. Okay, so what do I want to do? I want to take the second derivative. So to do that, I need to first take the first derivative, f prime of x. That will be 5x to the fourth minus 30 times 3 is 90 x squared. And then I want the second derivative, so we just differentiate again. F double prime of x is 20x cubed minus 180x. And almost certainly what I want to do is factor this. So let's factor out as much as we can. This will be 20x times x squared minus, if we pulled out 20 from this, 9. X squared minus 9. And that's still not fully factored. This is a difference of two squares. This will be 20x times x minus 3 times x plus 3. Alright, so what do we do now? How do we solve these inequalities? Well, we take the domain of the function. We take the domain of the function, and we plot all of the zeros. All the zeros are the points where it's undefined. So the zeros of the second derivative now, right? I'm testing the second derivative for if it's positive or negative. So I'm taking all the zeros of the points where it's undefined. This is a polynomial, it's defined everywhere, so I just need to take the zeros. And the zeros are easy to read off since it's fully factored, right? Either x is 0, x is positive 3, or x is minus 3. So 0, 3, and minus 3. Alright, this is how we solve these inequalities. I'm asking, is this positive or is this negative? Well, we come in here and we take all the zeros and all the points where it's undefined. We plot it on the domain of this function, and now we just test individual points in each subinterval, right? Just like we did before with increasing and decreasing. So let's test some points. Take something between 0 and 3. Let's take 1, because it's a nice easy number. So f double prime of 1 is, it might actually be easiest to plug into, let's plug into this function. We've got 20 times 1, 20 times minus 2 times 4 is, all I care about is the fact that this is negative. That's negative. So since my second derivative of 1 is negative, it's negative on this entire interval. Means what? Means it's concave down there, right? We'll plug in another number, something bigger than 3, how about 4? Well, now we can just start, let me not plug in these actual numbers. Let's think about doing this in our head, right? It's actually very obvious what happens. If you plug in 4, I have 20 times 4 is positive, 4 minus 3 is positive, 4 plus 3 is positive, so this is something that's definitely bigger than 0. So we plugged in 4 and we saw it was positive at 4, so it's positive from 3 to infinity. Means it's concave up there. And if we just keep checking numbers, f double prime at, say, minus 1. What do I have? I plug that in and I get minus 20, so negative. Minus 1 minus 3, that's a negative. Times minus 1 plus 3, that's positive. So negative times a positive is, how many negatives do I have? Negative, negative, positive is positive. So we plugged in minus 1, and you can plug in the actual number and figure out what the value it actually is if you want, but all I care about is it positive or negative. So we saw minus 1 was positive, so it's positive from minus 3 to 0. And last but not least, plug in something less than minus 3. How about minus 100? Because this will make it very obvious what happens. Here I'll have 20 times minus 100 is a negative number, minus 100 minus 3 is a negative number, minus 100 plus 3 is a negative number. Negative times negative is negative. So it's negative along here as well. And that's all the work we need. Alright, so where's it concave up? Concave up. Well, our table here, or our subintervals here, tell us exactly where it's concave up. The second derivative is positive from -3 to 0, so it's concave up there, and positive from 3 to infinity, so it's concave up there. So it's concave up from -3 to 0, and 3 to infinity. And it's concave down from, the second derivative is negative from -infinity to -3. And it's also negative from 0 to 3. So it's concave down from 0 to 3. And if we wanted to do a little bit more work, the inflection points are the points where it changes concavity. So it changes concavity at -3. When x is -3, I'll have to work out the y value. So x is -3 and f of -3. It also changes concavity when x is 0, and it changes concavity when x is 3. So 0 and something, and 3 and something. And we'll just work out these points really quickly. Let's see, I lied, these are huge numbers. If you plug in -3 into this, so plug it back into the original function, I want the y value, you'll get 567. 0 is the only easy one to plug in. Plug in 0 into this function, I've got 0 minus 0, so another inflection point at 0 and 0. And if you plug in positive 3, you get minus 567. Alright, so this question of figuring out where a function is concave up or concave down is almost identical to figuring out where a function is increasing or decreasing. Right? The only difference is we work with the second derivative instead of the first. Alright, last up in the section, we've talked about concavity now, but the section was titled Concavity and the Second Derivative Test. So here is the famous second derivative test. And I'll just give you the test right off the bat, and then we'll talk about it. So okay, here's our second derivative test. Remember what we were doing in the previous section, right? We were trying to identify relative maximums and minimums. Relative maxima and minima, I suppose I should say. But the way we did that is we found all the critical numbers, right? Critical numbers were candidates for maxes and mins. Or they could be neither, but if I have a max or a min, it must occur at a critical number. So then we had this question of, okay, we can find the critical numbers, but how do we tell, right? How do I tell if a given critical number is a max or a min or neither? And in came the first derivative test. The first derivative test answered that question for us. It says, if I know if my function is increasing or decreasing to the left and to the right of the point, then I can determine whether that point is a maximum or a minimum or neither. Well, the second derivative test provides us with another way of answering this question. It has its pitfalls, but it also has its very strong points. And for starters, it says, okay, so suppose f prime of c is 0. What does that mean? That means c is a point where my derivative is 0, so it's a critical number. The catch here, the pitfall, is this test only applies to one type of critical number. The critical number is where my derivative is 0. Remember, we had the other flavor, though, the other type of critical number, which is maybe my first derivative doesn't even exist. That's another critical number. So the second derivative test only applies to this type of critical number. This is the zeros, the horizontal tangent lines. The good news, though, is that usually most critical numbers come in this type. So suppose I have a critical number, c, then if my second derivative at c is positive, then I can actually classify this critical number. I can say that I have a relative minimum at c. Why is that? Well, okay, here's c. Right, well maybe there's x equals c. And I know the tangent line at c is horizontal because my derivative here is 0. So I have a function with 0 derivative at c, but my second derivative is positive. What does that mean? That means my function is concave up. So horizontal tangent right here, function has to be concave up. Well, the only way that can happen is if my function looks like that, because that's concave up, right, with a horizontal tangent line right here. Well, if my function looks like this, and that's c, then obviously that's a minimum, right? So this is a really nice test. It says, okay, take your critical number corresponding to a horizontal tangent line, just plug it into the second derivative. If the second derivative is positive, then you're a minimum. Vice versa, if my second derivative is negative, okay, second derivative is negative, I've got horizontal tangent line again. Horizontal tangent line. Second derivative at c is negative, then it must be concave down. The only way it can be concave down and have a horizontal tangent line there is if it looks like that. So this is a point at the top of a hill, so it must be a relative maximum. Unfortunately, this sort of works the other way around than you would think intuitively in your mind, so you'll just have to commit this to memory, right? A lot of people want to think second derivative positive, positive is maximum, negative would be minimum. It is actually the other way around. If the second derivative is positive, it's a relative min. So it's the opposite of what you'd think or hope, but just commit this to memory. Right, so second derivative is positive, that means it's a minimum. Second derivative is negative, that means it's a maximum. And you might run into this situation, you plug in your critical number c into the second derivative and you get 0, or it doesn't exist. And in this case, the test it's inconclusive. It doesn't tell you anything. But that's okay, because we can still hope to classify c as a max or min or neither by using the first derivative test. All right, there are other options. This is just another way of going through this classification process. Again, the downfall is that it only works for one type of critical number. The other downfall is that you take the first derivative, maybe that's a very complicated function. Differentiating again to get the second derivative, that might be a long process, right? That might take quite a while to do. Usually it doesn't though. Usually it doesn't take very long to differentiate again at all, so it's really nice to go through this process, and it's faster than figuring out all the intervals in which your function is increasing or decreasing. So it's usually quite a nice test to use. But if you do find that taking the second derivative takes a while, then don't do it. Just go to the first derivative test, right? There's two different ways to achieve the same goal. Okay, so here's our function, f. It's a polynomial. I could make this a business application if I wanted. I could make this a cost function and say let's find all the relative maxes and mins of this cost function. But it's the same process, right? We just have a function. I want to find all relative extrema, so the first step is I need to find all the critical numbers, right? Because those are the candidates for possible relative extrema. So we'll come in here and try to find the critical numbers, meaning I need the first derivative. It's a polynomial, so it's not too hard to differentiate. Minus 6x squared plus 6x plus 72. This is defined everywhere, so I don't have to worry about points where my derivative is undefined. I don't have any critical numbers like that. But I might ask, what are the zeros of this function? So I want to factor it. First things first, let's divide both sides by minus 6. this will be x squared minus x minus, I think this is 12 equals 0. 72 over minus 6 is minus 12. And hopefully this factors. I think it does. It should factor as x times x multiplies together to give minus 12, adds together to give minus 1. We're looking at minus 4 and plus 3. So I have two critical numbers. Right, when can this be 0? This can be 0 when x plus 3 is 0, so x is minus 3. Or when x minus 4 is 0, so x is positive 4. So I have two critical numbers. And luckily, they are both of the type that the second derivative test can handle. Right? They are zeros of the first derivative. So I can use the second derivative test to classify them as relative maxes or mins. Right? Assuming, you don't always have to go this route, but I'm going to go this route, one, because we just taught the material, but two, because differentiating this function again is very easy. Right? It's just a polynomial, so the second derivative is minus 12x plus 6. Okay? So, we'll plug in our critical numbers. We'll plug in minus 3. What do we have? Minus 12 times minus 3 plus 6. That's minus times minus is a positive number, plus 6. This is clearly positive. Right? What is it actually? It's 42, I think. But it's clearly positive. So that means that minus 3, if my second derivative is positive, minus 3 corresponds to a relative minimum. And so f of x has a relative minimum at x equals minus 3. And of, right, the question was to find all the relative extrema. So it doesn't really, it's not asking us where it occurs, although all the work goes into figuring out where it occurs, but it's of f of minus 3, which equals, I don't have a calculator on hand, so these are pretty big numbers. Let's see, minus 2 times minus 3 cubed is minus 27, plus 3 times minus 3 squared is 9, plus 72 times minus 3. These are pretty big numbers. This is 3 times 27 minus 3 times 72. Obviously you would just plug this into a calculator, right? But I don't have one, so I'm stuck doing this in my head. If I factor out a 3, that's 3 times 27 minus 72. That's 3 times 27 minus 72 is 65, 45, minus 45. I think, assuming my arithmetic has been correct here, that is minus 135. Okay, so we had a relative minimum at minus 3, and the value of that relative minimum, assuming my arithmetic was correct, is minus 135. We'll check the other point. Right, this is a really beautiful test because all you have to do is plug your critical numbers into the second derivative and ask, is it positive or negative? So f double prime of positive 4 is minus 12 times 4 plus 6. This is a really big negative number plus 6. This is clearly negative. So f of x, has a relative, negative second derivative means we have a relative max, has a relative maximum at x equals 4 of f of 4 which you plug in 4 into the original function. I actually have this one written down this time because I knew it was hard to compute, is 208. So we had 2 critical numbers, and now we've classified them. And that can be it. That's the only possible relative maxes and mins. Really nice test. Again, the downfall is sometimes differentiating twice can be hard. Right? And the example I've done here is a polynomial. Polynomials are the nicest possible functions. You'll see more for homework where maybe it's a quotient or it includes exponentials or something, but the process is still the same, right? The process is the same. Differentiate, find the critical numbers, differentiate again to get your second derivative, and plug those critical numbers in and ask, is it positive or negative? Thanks.